So in today's portion, let us study about the Kepler's laws of planetary motion from our next concept of the chapter gravitation. So hope you all will be enjoying this video. In 1609, Johannes Kepler published his book Astronomia Nova of his 10 years of studies. He used and studied observations of his mentor and employer Tycho Brahe. So, about the Kepler's laws, the story starts with the Ptolemy's geocentric theory. Ptolemy gave the geocentric theory. According to this theory, the Earth at the center of the universe, the planets, stars and sun revolve around the Earth in circular orbits. This was the geocentric theory considered in the first time era. Then comes the Polish monk Copernicus. Copernicus, he stated about the heliocentric theory, where he said that Earth is not at the center, but he put the sun at the center. The sun is at the center of the solar system, and that all the planets including Earth revolve around it in circular orbits. This was the heliocentric theory, which later on was studied by Tycho Brahe. So this study of Tycho Brahe were further processed ahead by Johannes Kepler, and where Kepler studied about the orbits of Mars too. And after studying the orbitals, he gave the three laws of planetary motion. Those are law of orbits, law of areas. When Kepler started studying about the planetary motion, he studied the planet Mars too, and he stated that the orbits are not circular but they are elliptical. Ellipses are type of conic sections, they are the elliptical orbits, where he stated that these elliptical orbits which have two foci in them, F1 and F2, where sun may be at any one of the foci and the planet from these foci is always equidistant. For this he says R1 plus R2 is equal to constant. Also he states that if the foci are both very closed or overlapped, then this elliptical orbit looks similar like a circle. It is a conditional term. After justifying this elliptical orbit, he gave the first law of Kepler, that he states the orbit of every planet is an ellipse with the sun acting as one of its foci, where sun may be at any one of the foci and the planet when closer to the sun is in perihelion, and when is further away from the sun it is in aphelion. He also states that the distances are equivalent for most of the planets, but in such cases the eccentricity is very low, and ellipses they are very highly eccentric. The skinny and longer perimeter of the circumference is known as the eccentricity. Let us study the ellipse now by the given activity.
Let us conduct an activity to better understand this. Fix a drawing sheet to a pin board. Select 2 points F1 and F2 on the board and fix 2 pins at the points. Take a string of finite length and pass it through a small ring. Fix the 2 free ends of the string to the 2 pins located at F1 and F2. Pass a thin pencil through the small ring. Stretch the string taut at the tip of the pencil and draw a curve on the sheet by moving the pencil as shown. Take care that the string is taut while you draw the curve. The closed curve you observe is the ellipse. Points F1 and F2 are called the foci. The midpoint of AB, which is denoted as O, is the center of the ellipse. For any point P on the ellipse, the sum of the lengths PF1 and PF2 is constant. So, As per the first law, the Sun is at one of the foci of the ellipse and the planets rotate around it in elliptical orbits. Also note that sum of the lengths PF1 and PF2 is...
The second law of Kepler states that the orbital speed of a planet will depend on its distance from the Sun. If it is away, it is slower, and if it is closer, it is faster. Though it may be anywhere, it covers equal areas of the ellipse over equal time intervals. Either it may be in the closer region or either it may be in the furthermost away from the Sun region. When the planet revolves in the elliptical orbit, it covers the portion. Let us consider that it covers a portion of area CD in particular time, and it covers portion of area NM in particular time. Though the aerial velocity is different, but the area covered by them is equivalent. So we may say that the planet sweeps equal areas of the ellipse over the equal time interval. Now the third law of Kepler states us that the square of any planet's orbital period will be proportional to the cube of the semi-major axis. In simple words, when we tell it, we can say that the time period, the square of time period is proportional to the distance cube, where we say that the time period is given by P, in which we use the term T in our books, and the distance is given here by A. In books it is used as R. So T square is directly proportional to R cube. These are the Kepler's three laws of orbits. Let's revise the Kepler's laws of planetary motion in short. Johannes Kepler published three laws of planetary motion. The first two in 1609 and the third in 1619. The first law: the orbit of a planet is an ellipse with the Sun at any one of the foci. The foci may be at any one point of the ellipse. The second law: a line segment joining a planet and the Sun sweeps out equal areas during equal interval of time, which shows that the planet covers equal area within the equal months of time interval. The third law: the square of the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit, where p square upon a cube is equal to constant in